Welcome back to another lecture. And in this lecture, we are going to learn about graphs. I've decided to teach graphs in two parts. So this is the part one, and in this one, we are going to mainly focus on the theory or the conceptual part. And in the next one, we'll focus on some advanced topics and the implementation parts in the codes. So what actually is graph? Graph is a set of nodes and edges. So nodes are basically the vertices or the corners, and edges are the lines that connect these nodes. So these edges can be weighted or not. Weighted edges means weighted edges means that these edges have some weight like 5 or 4. For example, if you want to visualize it better, you are going from point A to point B. So suppose this is point A and this is point B, and you're going from here to here. So it can carry some weight. For example, it can take some five units of cost or anything. So for example, 5 rupees. So it would take you 5 rupees to reach to point B from point A. So this is a connection of graph, and these can have weights or not, and these can have directions or not. This is an undirected graph in which the graph has no directions. For example, if the edges are pointed, that only from point 1 you can go to point 2 and you cannot go from point 2 to point 1. This is a directed graph. And other terms include path. For example, if you want to go from point 1 to point 5, you can take this path from 1, 3, 4, and 5. So one path is 1, 3, 4, and 5, and another part would be 1, 4, 5, which is the shortest part, and another would be 1, 2, and 5. So these two reach in just 3 steps. This will take 4 steps, or these two will reach in 2 steps, and this will reach in 3 steps. So these are the various paths. Cycle. Now, what is a cycle means that you can reach the original point from where you started. If you can reach back there, then you can say the graph is a cycle. For example, in this graph, I can go from point 1 to 2, then to 4, and then again to 1. So this is a cycle. Whereas if I make a graph like 1, 2, 3, if I make a graph as such, this is not a cycle because if I start from here, I cannot reach back to the same point. So this is not a cycle. Next, we have what is called as uh, adjacency or degree. So, what adjacency means that to the vertex 1, we have three adjacent nodes. You can see it is connected to 3 as well as 4 as well as 2. So, the degree of this vertex is 3. If I write it like this, the degree of vertex 1 is 3. So, we can see that the degree of vertex 2 is also 3. The degree of vertex 4 is 4 because it is connected to all the other nodes. And the degree of vertex 5 is 2. And when the degree of all the nodes is same, for example, if the degree of all the nodes is equal to 2 or 3 or n, we call it as a regular graph. Next, we have, so we've already seen weights. Next, we'll go to graph traversals. So we have mainly two methods for traversing graphs. One is the breadth first search, also known as BFS, and the other is depth first search. In breadth first search, what the algorithm says is, I'll first explain this, then you will automatically pick up on what is written here. For example, if I start traversing from point 1 and I want to visit all the nodes, see what traversing basically means. I already told you in the previous lectures is that you have to visit all the nodes, each and every node, and only once. So if I start from this, what breadth first search says is visit all the adjacent nodes before progressing. And just to hint it to you, we implement it using a queue. So let me put it in a queue. Firstly, we start with 1. The algorithm says visit all the adjacent nodes. So all the adjacent nodes means 2, 4, and 3. So let me write 2, 3, and 4. Then what it says next is pick one and complete exploring. Exploring means visiting all the adjacent nodes. So next one I'll pick 2 because this is a queue. So I can cross one out, which is in queue you know that it is first in, first out. So first we inputted 1 as it was a starting point. Next 2, 3, 4. So let's explore 2 next. So we'll write the adjacent nodes as 6 and 5. Because 1 is already written, you need not write it again. So after inputting 6 and 5, we can pop out 2. Next 3. We only have 1, which is 9. Next with 4, we have 9 and 8. 9 is already written, so you need not write it again. We write 8. Then for 6, we have 7. Then for 5, we don't have anything, so we can simply strike it out. And for 9, we have 10 and 11. And then for 8, we have 4, which is already done. For 7, we have 8 and 6, which is already done. And for 10 and 11, we have nothing. So we have successfully traversed this in a fashion of breadth first search. So if I go ahead and draw the spanning tree that we made out of this using a breadth first search. What spanning tree means is that we have all the nodes in it, but the edges are less than the number of nodes. So if the number of edges is n, the edges will be n minus 1, meaning there is no cycle in a spanning tree. And so first we visited 1, then we visited, sorry, then we visited 2, and then we visited 3, and then we visited 4, and then 6, 5, 9, 8, 7, 10, 11. So this is the spanning tree that we obtained by using breadth first search. And you can notice in this that there existed a cycle in this. This was a cycle. This is a subset of the graph, subgraph, which was a cycle. But the spanning tree we do not have that. So that is what is a spanning tree. So I hope you understood what breadth first search is, and it is implemented using a queue. Next up, we have depth first search. This is the second algorithm that is used, and in this, what we do is visit. Okay, I'll explain this as we solve it. So in this, first we visit a node, pick one up, and we implement it using a stack. Okay, so let's keep a stack here. And first we visit a node, pick one of the explore nodes. So first start with 1. We input 1 into this, and then we can pick any of the adjacent nodes. Pick any. So we have two adjacent nodes here, 3 and 2. Let's pick up 2. So after picking up 2, then we will pick up again any one of the adjacent nodes. Next we have explore that node and pick up another one of the unexplored nodes. So we have 4 or 6 or 5. Let's pick up on 6. After picking up on 6, we will go to 7. So once we reach 7, 7 has no unexplored adjacent nodes. So we can pop out 7. Then we come back to 6, and then even 6 does not have any unexplored adjacent nodes. So we'll pop out. Then we'll come back to 2. So we've gone in this direction. We came from 1. So we have 4 and 5 as options. So let's go with 5. After going with 5, we go with 8, and then we pop out 8 and 5 as well. So next we go with 4, and once we go with 4, Now let's go with 3. So after going to 3, 1 is already explored and so there is no way, so we pop out 3. And for 4, then we go for 9. Just imagine this as a part of the stack. Then we go to 9 and then to 10. Then we pop out 10. Then from 9 we go to 11. Then we pop out 11. Then we pop out 9. Then we pop out 4. And then 2. And then 1. So in previous lectures, you also already learned about backtracking. So you can relate it easily if you understood what backtracking was. So this is what depth first search says. And now let's move on to minimum cost spanning tree. I already explained it to you what a spanning tree was. So what a minimum cost spanning tree says is in a weighted graph, if I want to find the way in which I want to find a spanning tree in which the cost is minimum because that is the case of optimization. You already learned the brute force method, the greedy, dynamic, and everything. So why do we do this? We do these things to optimize. When we solve a real world problem, mostly our problems are with optimizing. Either it is minimizing or maximizing anything. And both of these comes under optimizing. For example, I want to go from point A to point B in the minimum time or in the minimum cost. Uh, or without any traffic or anything. So these all comes under the case of optimization. So for example, in this graph, I have 6 nodes. So here vertices are 6. And I already told you the edges has to be n minus 1. So in this, the edges will be 5. So this is also a minimum spanning tree. Here, no cost is allotted to the edges, so this cannot be a case of minimum cost spanning tree, but yes, this is a spanning tree. And you may wonder why did we only miss out on this edge? We could have left this edge as well, meaning it would have looked something like this. So yes, even this is a spanning tree for this problem set, and we'll have many more. Like if I miss out on this edge, if I miss out on this edge, or this or this. So the total number of spanning trees that a graph can has is, for example, in this we have to choose the number of edges. Total edges is 6 and from those we have to choose 5. So 6C5 would be the case in this. But what if I had a graph like this? So there exists a cycle in this. There exist 2 cycles in this. So we'll have to subtract the number of cycles from it because now I have more options for this. I can also have this as a minimum cost spanning tree here. If you want see 1 2 3 4 5 and 6, so I have 6 edges even here. So I'll have to subtract the number of cycles from this. So now let's give it some weights, and I have a number of vertices as 4 and I have some weight allotted to each of the edge. This, keep in mind, this is a undirected graph, meaning there is no direction of the edges. I can go from 1 to 2 or 2 to 1. So basically, if it is an undirected graph, imagine it as a bidirectional graph, directed graph. So I can just visualize it as bidirectional for every edge. Okay, so if I want to find out the minimum cost spanning tree for this, see, there are costs allotted here. So first let's draw any spanning tree. 1, 2, 3, 4. This is a spanning tree. Its cost is 2 plus 4 plus 7, which is 13. Another spanning tree would be, this is another spanning tree. 2, 1, 3. So this would add up to 7, 1 and 2, which is 10. So this is lesser cost than this, but I want to find the most optimized solution. I do not want to find out all the subsets. See, brute force, you already studied about brute force too. So what brute force does is It finds out all the possible subsets, or out of the sample space we find out everything, and then we select the best thing. But it will give you a time error, and it is too costly for resources like time and space. So to value these, we have greedy methods or dynamic methods. So here we have two greedy methods, algorithms, prims and Kruskal's. I'll explain it to you using the same example so you understand what the algorithm is. First, if I just want to find out the answer for this without any algorithm, we will simply think, okay, let's select this one because it is minimum one, and then let's select this, and then I'll select this. So if I select this, even this is a spanning tree because it visits every edge, and it's uh, and the number of edges is less than the number of nodes. So here the cost is only 6, but we eyeballed it and found it through some greedy method that we created on our own. But to find out if it works for everything, we have prims and Kruskal's. So what prims algorithm says is, firstly, select any node. For example, let's select 1 as a starting node. Then from 1, we'll select the minimum cost adjacent, or the minimum cost edge which is connected to 1. From 1, if we can go to there and it is minimum, then we'll select. For example, the minimum cost here would be 10. Okay, so let's go and draw 10. Next, from 1 and 6, we'll select the next minimum edge. Like the next minimum edge would be 12, but it is not connected to either 1 or 6. So we'll have to find the edges. Out of the edges connected to 1 and 6, we'll have to find the minimum one. So we have our two options, 25 and 28. So 25. So from here we can select 12 or 24 or 28. Let's go with 12. From here, and then we can again go to 12. Then we can go to 16, and then we go to 14. So if I'm correct, we have visited all the nodes 1, 2, 3, 4, 5, 6, 7. So we have visited all the nodes and we have done it using a greedy method, meaning we have already defined some predefined rules and we follow it every time at every decision making point. We follow our predefined rules, and using that we obtain our goal. So if I add 10 plus 25, 35, and this is 47, 59, 59 plus this is for 30. So this adds up to 89 if I'm correct. 10, 35, 47, 59, 59 plus 30, 89. So now let's go and understand what Kruskal's algorithm says. Kruskal says select any edge. For example, let's start with this, and then select the minimum edge which comes. At every step, select the minimum edge. That is what Kruskal says. So if here the minimum edge is 10. Next, Prim said select the edge only which is connected to the previously selected nodes. What Kruskal says is select the edge with the minimum cost. Need not to be connected to our nodes. So I'll select 12 right here. So it is connected with 3 and 4. Next with 5. Again we go with 12. So this is done. This is done. 10 is done. The next minimum is 14. So it is between 2 and 7. So even 14 is done. Next is 16. And then it is 18. So Kruskal's only condition is that while drawing the edge, if it forms a cycle, do not include the edge. If I draw 18 right here, this is a cycle, and Kruskal says never make a cycle. So if it is implying that it will create a cycle, do not include it in your edge list. So cross 18. Next we have 24. And 24 also creates a cycle. This would be a cycle. So do not include 24. And we have 25. So we received the same minimum cost spanning tree using Kruskal's too. So you can confirm this, and the edge cost would be the same. And what Kruskal says is only start with any point, connect the edge with the minimum cost, but if it is creating a cycle, do not include it. And what Prim says is start with the minimum cost that is connected to your node. That is the only difference. Now next we have Dijkstra's algorithm. This is a very popular algorithm used for finding minimum cost distance between any 2 points in a graph. And why this is important? Because this is a founding base of any graph question. For example, even when we use our GPS systems or Google Map system, we want to find out the minimum point from here to our college or some shop or anything. So it uses algorithms like this to find out the point. We'll try and understand what this is. So what the basic logic says is if the distance to some point, if I can't directly reach to that point, but I can reach it via some point. So for example, I'll explain this formula in a bit. This is the pseudocode, but first let's understand the problem. So for example, I'll calculate the distance from point 1 to every other point, from point 1 to 2 to 3, 4, 5 and 6. So what I'll do is I'll start with 1 and I'll mark the distances. I'll use a red pen. I'll mark the distances to the points which I can directly reach by 1. So I can reach directly to 2 and the weight is 2. I can reach directly to 3 and the cost is 4. Rest others I cannot directly reach from point 1. So I'll mark them as infinity. Now what this algorithm says is, so I've already explored 1, so I'll cross it. Next, let's say I'll explore 2. The cost to reach 4 from point 1 is infinity, but if I use it by go to it via 2, so it will be 2 because the cost till 2 is 2 and from 2 to 4 it is 7, so 2 plus 7 which is 9, it is less than infinity. So the cost to u point u for currently this is our u, so the distance to u which is written here plus cost of u to v, this is the cost of u to v. If it is less than dv which is infinity, then replace it by this. So we'll cut this and use 9 now. Next we have 3 uh, to node 3. So the cost is 2 plus 1 which will be 3 and the previously cost was 4. So if I go to point 3 using 2, it will be cheaper than directly going to it via point 1. So I'll cross this and mark as 3. So everything is done. So I'll cross out 2. Next let's explore 3. So from 3 I can go to point 5 and the cost would be 3 plus 3 which is 6, which is lesser than infinity. So I'll update it to 6 and there is no other point. Next I'll explore 4. Then from 4 we can go to point 6 which is 9 plus 1 which would be 10 and this was infinity. So I'll update it. I cannot go to point 5 because the direction is from here. The direction is not from 4 to 5, it is from 5 to 4. So even this is done. Uh, Next I have point 0.5. From point 0.5 I can go to point 0.6 which is 6 plus 5 which is 11. But this is already 10, so there is no need to update it. And now I've successfully visited every node and updated the final values. So from point 1 to 2 the cost would be 2 which is the final cost here. To 3 it would be 3. To point 4 it would be sorry, this would be 9, or wait, uh, 3 plus 6 and then 2. Okay, so if I visit point 5 here first, so the one more set of relaxation I have to conclude. From 2.5, the cost is 6, and from 6, I can go to point 4 with 6 plus 2, which is lesser than 9. So the cost would be 8. So hence the cost is 8. Then to point 5, it is 6, and to point 6, it is 9. So from here, I can again go to 8 plus 1, which would be 9. So the final cost is 9. So I'll have to check for relaxations at every step. After I've updated some value, I'll have to again check because the updated value will affect the new value. And once the values stop changing, it is constant after the iteration, then I can successfully stop it right there. I have another example here. This is a confusing graph, but it is a popular question for college perspective too. So let's start with point 1. From here, I can reach to point 2, which is 50. I can reach to point 4, which is 10. And anything else, I can reach to point 3, which is 45, and nothing else. So first, let's go to point 4. After going to point 4, I can see that the cost to point 5. Okay, let me mark these as infinity also. Yeah, so to point 5, the cost was infinity, but from here and here, I can go till point 5 for just 25. So I'll update it. Next, I cannot go anywhere, so I'll check this out. Let's go to point 2 now. Uh, okay, first let's explore point 5 only. From point 5, I can go to point 3 for 25 plus 35, which would add up to 60. This is already 45, so no need. I can go to point 2 for 25 plus 20, which is 45. So I'll update this as 45, and there is nothing else. Next, let's go to 2. So from point 2, I can go till here, which is 45 plus 10, 55, no need to update. 45 plus 15 is 60, no need to update. So I can cross this out. Next, I'll go to point 3. From point 3, I can go to point 5, which would be 45 plus 30, which is 75, which is greater than 25, so no need. So these are the final findings. From point 1, I can go to point 4 for just 10, to point 5 for 25, to point 2 for 45, to point 3 for 45, and for point 6, it is still infinity. Infinity means that there is no optimal way, or there is no leave optimal, there is no possible way to reach point 6, because we can see that there is no incoming edge towards 6. So when there is no incoming edge towards 6, it is impossible to reach point 0.6. So it is marked as infinity only. The drawback of Dijkstra's algorithm is that if I have the uh, graph in which there is some negative edge, for example, this is point 1, 2, 3, and 4. Suppose this has 3, 1, 4, and this is minus 3. So when I apply Dijkstra's algorithm here, from point 1, let's start from point 1. So after starting from point 1, I can reach to point 4 for just 3. I can reach to 2 for just 1, and this is infinity. So from 1, I can reach till here for 5. So I'll update this, and nothing else. Then from 3, I cannot go anywhere. From point 3 to point 4, I can go for 5 minus 3, which is 2, which is lesser than this. So I'll cut this and mark it as 2. So before, I was greedier and I thought that it would be easy to reach point 4 directly using point 1, which would be the cost of 3. But if I go from 1, 2, 3, and 4, the path would be longer, but the cost is less as there is a negative weighted edge. So what this negative weight edge means in a real life? You might wonder, how can a distance be negative? But graphs not always represent the distance. For example, in business, you may count profit and loss. So there may be many pathways, suitable pathways for reaching your goal. But there may be some profit and some loss at every step. So to calculate those, we can use negative weights as well. It is not necessary that this is only for distance calculating. It can be used to represent any problem in the world. So that is the speciality of graphs. So here it calculates accurately key what is the condition. But what if I use update the value? I update this negative value to be, if I update the negative value to be minus 10, and this I'll update it to be uh, this I'll update it to be 20. So I'll reach from point 1 to point 4 for 20. I'll reach here for point 1 and then 5, and then 5 minus 10 is uh, minus 5. So this would be updated to minus 5. But what if this was already uh, 1 and this was, so I can reach here for 1, and from point 5 I'll update it to be uh, 5 minus 2 minus 2. Okay, so this is getting a bit confusing, so I'll just redraw it. See, it is not that Dijkstra's algorithm does not work for negative weighted graphs, but it may or may not work. So I'm trying to find a condition in which it does not work. This has minus 2 and this has 1. Yeah, so I can reach here for 1, this for 1, and wait, I'll mark it with a different color. This for 1, this for 1, this for 5. Now if I go from here to here, it would be 5 minus 2, which is 3, which is greater than this. So there is no point in going to this via this. I can directly go from there. But if this weight was minus 10, then this would have been 5 minus 10 and this would have been updated to minus 5. But what we already thought, we have checked this node and there is no need for checking this again. So the point was useless. Now if there was a way to reach from here to here, then this would have been, I'll go from this and then this. So it will be minus 5, and then here if I have some negative weight, it would have been minus 10. Again our previous calculation of 1 would have been cancelled out. So for negative edges, we have to be careful while using Dijkstra's. It may or may not work. So that's it for today, and in the next lectures we'll cover some more topics and solve some problems.